The strong nuclear force. So, a nucleus is made of protons and neutrons, and then there are electrons around the nucleus that are kept there. Now, in the nucleus, all you've got are positively charged protons and neutral neutrons that have zero charge. Now, since protons are positively charged, and two positive charges try and repel each other through the electromagnetic force, the nucleus ought to be pushed apart. It ought to be impossible to keep protons together in a nucleus. They should fly apart. So there must be another force that stops that happening, that's balancing out the electrostatic repulsion of protons in the nucleus. Now, one force that might be could be gravity, but gravity is too weak. The mass of a proton is only 1.7 times 10 to the minus 27 kilograms. So protons have a very small mass. It means the gravitational attraction between protons and neutrons and protons is too small to keep the nucleus together. So there must be another force. It turns out that there are four fundamental forces. Right? All the other forces that are ever mentioned are just aggregations of these. So pushes, pulls, upthrust, any force you can think of is actually just one of these forces. It actually means that there's no such thing as a contact force, because since all four of these forces are non-contact force, there's no actual contact forces in the world. So when you push something, it's just the electrostatic repulsion between the atoms in your hand and the atoms in the object that you're pushing. So the four fundamental forces that we know that exist in physics are the electromagnetic force, gravity, the weak nuclear force, and what's called the strong nuclear force. Of these, it is the strong nuclear force that holds matter in the nucleus. The strong force opposes the electrostatic force and keeps positively charged protons together in the nucleus. Now, the strong force is a complicated force. It is mostly attractive between nucleons. Nucleon is the collective word for any particle that's in the nucleus, so it means protons or neutrons. Both protons and neutrons feel the strong force. The strong force is the strongest force that we know of. It's very strong, but it only works at short distances. So it works at distances around about 1 times 10 to the minus 15 meters. That's called a femtometer. So, because the strong force doesn't work at sizes very much bigger than a few femtometers, that's why atoms are so small, because the nuclei of atoms, it's impossible to have protons and neutrons stuck together at distances where they're very much more than a few femtometers apart. So this is a graph of the strong nuclear force, and it's a little bit complicated. So you can see that we've plotted on the y-axis the force, and at the top, above the zero, the force is going to be repulsive, and below the zero is going to mean that the force is attractive. And along the x-axis, we've plotted the distance between any two nucleons. So let's say the distance between two protons, and we can see that as the distance between two protons increases, the strong force that they feel changes. So if they're very close together, the strong force is actually pushing them apart. Instead of attracting nucleons together, it pushes them apart. But as they get further and further apart, the strong force flips round and it becomes attractive. So between about 0.5 femtometers and about 3 femtometers, the strong nuclear force is attractive between nucleons, so it's keeping them stuck together. As it gets to about 3 femtometers though, the strong force just decays to be 0. So after about 3 femtometers, there's no strong force felt. So any two particles, if they're further away than 3 femtometers, they don't feel the strong nuclear force. So there are 3 different regimes. If a neutron and a proton, or a proton and a proton, or a neutron and a neutron are within 0.5 and 3 femtometers, then they'll be attracted to each other by the strong nuclear force. If the distance between the nucleons is less than 0.5 femtometers, they'll be pushed apart by the strong nuclear force because it's repulsive. And if the distance between them is bigger than 3 femtometers, then they'll feel no force at all, and it's as if the other particle isn't there. We can compare the strong force and the electromagnetic force. So if we had two protons, then they would feel an electromagnetic force between them that would be pushing them apart. And the electromagnetic force would always be repulsive between two protons because they're both positively charged. So the electromagnetic force never crosses over to be attractive. It's always repulsive, and it gets infinitely repulsive as the distance between the protons gets smaller and smaller. So the electromagnetic force is always repulsive, and it's only felt by protons in the nucleus because the neutrons have zero charge. The strong force is felt by the protons and the neutrons in the nucleus, and the strong force can either be attractive or repulsive depending on how far apart the nucleons are. You can see that the actual size of a nucleus is this equilibrium point where the two forces are balanced. So the point where the repulsion from the protons trying to push each other apart due to the electrostatic force is balanced by the attraction between them due to the strong nuclear force. That gives you the size of the nucleus when those two forces have cancelled out and the nucleus is in equilibrium.